Welcome to the exercises for Chapter 8. Let's begin with exercise 1. The goal of this exercise is to write a Python function that implements an algorithm that can solve mean value theorem problems. I described the mean value theorem earlier in this chapter, and I went through several examples. And so in this exercise, you are going to create a Python function to solve the mean value theorem problems. Now, this exercise, or the function that you create in this exercise, you are going to use for the next like 5 or 6 exercises in this chapter. So take your time working through this one and make sure that you get the correct solution so that your subsequent exercise solutions are also correct. Okay, so your Python function should take 3 inputs. The first input is a SymPy expression, so a symbolic object corresponding to the function. And then the second and third inputs into your Python function are the 2 boundary points at which to evaluate the function to solve the mean value theorem. Okay, so, and then here I've outlined the steps to implement in order inside your function. So I called the function solve MVT for mean value theorem. Okay, so step 1 is to get the derivative. You want to differentiate the function using SymPy. Step 2 is to find f of a and f of c. Remember, a and c are the 2 x-axis boundaries for the interval within which we want to apply the mean value theorem. Okay, and then step 3 is to create a symbolic expression, so in SymPy, for the right-hand side of equation 820. As a reminder, here is equation 820. So basically we have the derivative of the function, and we want to find the x-axis value b such that the derivative at that point at x equals b of the function is the same as the slope of the secant line between c and a. So this is the formula for the slope of the secant line between c and a. So it's the difference in the function values, or delta y, divided by the difference in the x-axis values, or delta x. So a symbolic expression for the calculation of the slope of the secant line. And then you want to solve for b in equation 8.20 using sim.solve. And then remember that to solve these equations, you can set the equation to be equal to 0 and input that into sim.solve. Okay, and then finally, you want to find the elements of b that are between a and c. And this step is important because you might get multiple valid solutions to this equation, right, to the right-hand side to solving for b. But we are not interested in all of these solutions to this equation. We are only interested in the solutions to this, so values of b that are in between a and c, so within our interval that we are considering for the mean value theorem problem. All right, so do all that, and then the output of your function is those elements of b. And then you can test your Python code on this function, 2x squared minus 3x plus 1, in the interval of -1 and 2. Now, we worked out earlier in this chapter that the analytic solution using calculus is 1/2. So we know that the correct answer should be 1/2. Your code for this Python function should take this as input and these 2 values as the interval for input, and it should output this. And if you get that correct, then you can be confident that you can move forward to the next several exercises using this Python function. So here you see my code. I define a standard Python function called solve MVT, where the inputs are f, that is the symbolic or SymPy expression, and a and c are the 2 numbers for the x-axis boundaries of the interval. Okay, so here is step 1, differentiate f. Pretty straightforward. Step 2 is to obtain the function values at a and c, because we need those values to do step 3, which is to calculate the slope of the secant line connecting A and C. Okay, so here I call this the right-hand side of equation, and this is the the left-hand side of this equation is f prime of b, like this. Okay, and then step 4 is to solve for b. So here I use sim.solve. And now this must be like I don't know how many times you've seen sim.solve so far, but quite a few. So you know that there are several ways to use this function, but the way that I tend to use it is if you have something like this. So the equation that you're trying to solve for is something that looks like this. What you can do is say basically subtract RHS from both sides of the equation, set it equal to 0, and that is implicitly the way that sim.solve is going to work for one input. Okay, and then the idea, just as a reminder of the concept of the mean value theorem, the values of b that solve this expression are the values of the function, or the x-axis values, where the derivative of the function equals the slope of the secant line. Okay, now here you can see I am converting this into a NumPy array because the output of sim.solve is a list. So I'm converting it into a NumPy array and then forcing it to be floating point operation, floating point number. Now, the reason why I do this is because I want to use this bitwise AND function here. So this line of code here, this little piece of code, is finding only the elements of B that are between A and C. So the elements of B that are greater than A and also less than C. And that's, I am selecting from this array in order to output those from the function. There's actually multiple ways you could have implemented this. So if your solution looks a bit different, then that's great. Maybe you have a little for loop over here that loops over all the elements in B and identifies individual elements that are either outside the interval or within the interval. Any way you choose to solve this is fine. Okay, let me see. I will run this cell here. Now, there's no output of this cell because I'm not actually calling this function. I'm just creating the function. Okay, and then here is where I set it up for the test run. So here I create a symbolic variable x. Here I define the expression, the two bounds, and then I call this function with, call the Python function with the math function and the two bounds. And if all goes well, we should get the answer of 1/2, which is the correct solution to the mean value theorem problem for this equation. Exercise 2 of Chapter 8 follows directly from the previous exercise. In fact, this exercise is basically continuing where we left off from Exercise 1. So in Exercise 1, we created a Python function that solves the mean value theorem problem for a given function and two interval bounds. And then the result of that previous exercise was purely numeric, right? We just got a result, a number at the end. So the goal of this exercise, exercise 2, is to take that output of that function and create a visualization. And your visualization should include the function itself, the secant line connecting the 2 points A and C, and also the tangent line at point B. Okay, so I'm going to call that function, I'm going to name that function MVT and plot. So mean value theorem and plot. And the idea is that we input a symbolic expression for a function and two interval bounds. And then, basically this code we are going to continue using for the next several exercises. And in fact, the output, once you get this working, then you can create figure 8.8 in the text. And that looks like this. This is figure 8.8, and this is the successful result of solving this exercise. So you see the function here, you see the function being drawn here, and the black line here is the secant line connecting points or interval bounds A and C. And the idea is that our Python function determined that this point here, when x equals 1/2, that is the point where the derivative of the function, which is the same thing as saying the tangent line of the line going through this point, is the slope of the tangent line is the same as the slope of this secant line. Okay, and that's where we are here. So I create this new function, MVT and plot. You can see the inputs are the same as the solve MVT function that I created in the previous exercise. And in fact, what I do here, like right in the very beginning of this function, is call that other function from the previous exercise and get the solutions, x equals b. Okay, and then, everything else is basically just visualization. So I'm converting the expression into a lambda function so that we can get NumPy arrays out of this function in order to plot with matplotlib. And then I'm also getting the derivative as a lambdafied function. Okay, and then here I'm getting function values. And I'm choosing to use, linearly spaced numbers between the first interval boundary -1 to the second interval bound +1. Okay, so it's a -1 to c +1, and those are the x-axis values that I will use for visualization. Here I plot the function. Here I plot dots. You can see these are black circles with white marker faces for a and c. So x equals a and y equals f of a, and same for c. Here's the secant line. So this is the line that goes on the x-axis from a to c, and on the y-axis it goes f of a to f of c, using this lambdafied function from the SymPy expression. And then here I plot the tangent lines. Now, notice there's only one secant line to plot, right? Because we specified the two bounds to plot a secant line between, but who knows how many points in the derivative or in the function satisfy the mean value theorem. There's not only going to be one single point. Sometimes there might be in this example problem with this example function. There is, but it's just how it happened to work out here. So basically, we need a for loop to plot all of the tangents for all the points that solve the mean value theorem problem. Okay, and then, this is just making the plot look a bit nicer. Okay, run that code. Now, this code cell doesn't do anything because, I'm just defining this function. So therefore, here I'm going to actually call the function using these variables that I defined in the previous exercise. And that's the function that creates the figure that I just showed. Okay, very nice. So this makes it really easy now to explore other functions and other boundaries. And that's what we are going to continue working with in the next exercise. Now that we have Python functions to solve mean value theorem problems and also visualize the solution, we are going to explore different math functions using these Python functions. So in particular, there are 3 math functions that we are going to explore in this exercise, exercise 3. So 2 of them you see visualized here. So this one is the function 2x cubed minus 3x squared plus 1 using the interval bounds of -1 to +2. Okay, so that's one thing we're going to do. And then the sine function, so sine of x, in the bounds, the interval of 0 to 1.8 pi. And if your code from the previous 2 exercises was correct, then you should be able to produce figures that look just like this. Okay, and then the third math function to examine is this one here. So 2x divided by the quantity 2x squared plus 1, and then all of that business squared in the interval of -2 to +1. Now, when you try to run this, you are going to run into some issues. In particular, the Python function is probably going to crash, and your goal is to figure out why the Python function crashed when trying to solve the mean value theorem problem for this equation. Okay, I'm going to discuss this error and how to resolve it in a moment when I show you this in code. Now, we've already written a lot of code for exercises 1 and 2, so there isn't a whole lot of new code to write here. In fact, all I'm doing here is rewriting the expression, listing these bounds, and then, calling this function that I already created. Okay, so yeah, that gives this result here. Not much to say about this, except you can see that there are two tangent lines being drawn here. So that means that there are two valid solutions to the mean value theorem problem. There are 2 points on this function where the derivative at that function at those points equals the slope of the secant line from -1 to +2. All right, and then we have a sign. This is fairly straightforward. Again, here we see that there are 2 solutions to the mean value theorem problem. Okay, and here we have this funny looking expression here. All right, so before getting to before trying to solve the mean value theorem problem, I just want to have a quick plot so we can visualize this function. And basically what I want to convince you of here, what I want you to see is that this is just a sort of regular, normal looking function. There's nothing particularly weird. There's no infinite discontinuities or oscillating discontinuities. It's not a piecewise function. Nothing crazy about this function, at least based on visual appearance. Okay, so now let's see what happens when we try to run the mean value theorem code that we've gotten before. So we get an error, and let's see, what is the error message? The error message is cannot convert complex to float. So what does this error message mean, and where does it come from, and how do we resolve it? Okay, well, digging into this function, here I'm just rewriting pieces of the code to solve just the one specific part of the mean value theorem problem, where we build the right-hand side of the equation to find b, and then we try to solve it. Okay, so first I'm going to just run this code here and see that this works fine. So there's nothing wrong with this code here. And now let's see what these solutions actually are. So all I'm doing here is just printing out all of the solutions. And here we see that there are multiple solutions. There's 6 solutions in total. And you can see that these 2 are real valued and these 4 are complex valued. So they're complex numbers. There's a real part and an imaginary part. And this I is the imaginary operator. That's the square root of -1. Now, there's lots of interesting things that could be said about this that you would learn about in like an advanced algebra course. The fact that, when these solutions are complex, they come in conjugate pairs, which means that the real parts are the same. The imaginary parts have the same magnitude, but the signs are swapped. So those are complex conjugates. But we are not going to discuss those here. That is not relevant for this exercise or this book. Mainly, what I want to demonstrate is that the problem here is that we got solutions to this algebraic problem that were complex valued. And we only want to consider the real valued solutions to this problem. Okay, so this is the issue. This is the source of the error. And now the question is, how can we fix this error? There's a couple of ways that you can fix this error. One is by going back into the function. So now I'm scrolling up to the Python function that I wrote for exercise 1. So you could basically add some code in here. We could call this like step 4.5 or something, where you loop through all of these solutions and only pick out the ones that are real valued. So if they are complex valued, then you remove them from inside this function. That is one way to solve that. And if you would like to code that, that's great. I definitely support that. What I'm going to show you is another way to resolve this issue in SymPy, and that is by redefining x. So x equals sim.symbols x, but now I'm going to tell SymPy that x must be real valued. So x can only be considered in the field of real valued numbers. That is going to exclude any complex valued numbers from the solution. Okay, and now notice the code ran fine. We don't see any error messages. And here we get the plot. And this is the solution to the mean value theorem problem when we are constraining ourselves to real valued problems, real valued solutions. Okay, and then here I'm just going to run this code again. And here you see we only get the real valued solutions here. We don't see any complex valued solutions. Exercise 4 of Chapter 8 is continuing along the lines of using our Python functions to solve and visualize the mean value theorem problems with a different math function. In particular, try to work with this deceptively simple trig function, cos of x squared, in the interval of x is in between minus pi over 2 and 6 pi over 7. Okay, so the goal is to solve the mean value theorem problem for this function and this interval. You will discover that SymPy cannot do this. You're going to get an error message coming from your code. Now, this is a different problem as in exercise 3. So in the previous exercise, we encountered some issues. We were able to identify the source of those issues and resolve that issue. But here you're going to come up with another problem that is different from the problem in the previous exercise, okay? So after some digging, you will eventually find an error message in Python that looks like this. No algorithms are implemented to solve this equation. And basically what this Python error message is telling you is that SymPy is unable to find an exact solution to this equation, minus 2x times the sine of x squared equals 22 divided by 243. What a weird fraction. And here really the problem is that it is not possible to isolate x on one side of the equation. Okay, so that means that we cannot come up with an analytic solution, an exact solution to the mean value theorem problem. And so what we are going to do instead is come up with an empirical solution. So numerically approximate the solution, but don't worry about that yet. That is for the next exercise. What you want to do in this exercise is basically make sure you understand how to investigate your own math algorithm in order to come up with the exact problem that the function is running into. Okay, so here is the function as a symbolic expression. Again, variable x is a symbolic variable x. I created it in previous exercises. Okay, and here are the bounds that we are going to use. Here I'm just making a quick and dirty plot just so you can see what this function looks like. And again, this is kind of similar to how we started investigating the error message from the previous exercise. You want to start by looking at this function and just see what this function looks like. Maybe we're going to run into some problems because there are weird discontinuities inside the interval. But that's not the case. This is a continuous function. Just visually, it doesn't look like there's anything horribly wrong with this function. It's just the cosine of x squared. So it's defined for all of these points. There's no discontinuities. It's not a piecewise function. So it seems like the mean value theorem should work fine. The issue is, well, okay, let's see. Here we get to the error message. The issue is that SymPy is not able to come up with an analytic solution because basically there are multiple sources of x that cannot be separated. So it's not possible to isolate one variable x in this equation. Okay, and this is really the, let me see. This is the key part here. So let me uncomment this. And I can also comment out the plot. Okay, so here I'm just, again, like what I did with the previous exercise, I'm just writing out these different pieces of the mean value theorem algorithm in order to determine the expression that we need to solve for. So this is the expression. This is the derivative, and this is the right-hand side of the equation, which is actually just this. So it's the slope of the secant line from A to C, right? So here we have the change in x in the denominator, and in the numerator, we have the change in y for the function evaluated at points A and C. So that is the right-hand side of the equation, and we need to know where does x, what values of x make this equation true? And again, I've repeated this before, but what we really want to solve is this, right? And then these solutions to this expression, that the values of x that make this true, that is what gives us the values of b that we want to solve for in the mean value theorem problems. Okay, but so the way that this actually gets implemented is by subtracting the right-hand side from both sides and setting this equation equal to 0, and then we use sim.solve. Okay, so this is the equation that SymPy is unable to solve. And here, this is just to show you isolating this particular problem. This is where the error message is coming from. In the previous exercise, we discovered that there is an equation that SymPy cannot solve an exact solution for, which means that our code for solving mean value theorem problems did not work. And so at the end of exercise 4, we were just kind of stuck. There was just no way to solve that equation analytically to get an exact solution. And so that brings us to exercise 5 here in this video. So what we are going to do in exercise 5 is basically solve the same equation, so solve the same mean value theorem problem for cos of x squared in this interval. But now, instead of trying to get an exact solution in SymPy, we are going to get a numerical approximation using the grid search algorithm that you learned about in Chapter 6. This is a really great exercise because you have to integrate concepts and code about numerical approximations and the grid search method from Chapter 6, about critical points from Chapter 7, and about the mean value theorem from this chapter, Chapter 8. So the goal is deceptively simple. Write code to solve the mean value theorem problem for the equation and interval that I just went back to from the previous exercise. Now, don't worry about writing code that will work for any possible function that you can come up with. If you want to do that, then that's great. But for this exercise, you just have to focus on this specific mathematical function in this specific bound and write your code to solve this particular problem. Okay, there is a lot of coding that's involved in this exercise, but as I said, there isn't a whole lot of new material conceptually, so you can find the appropriate code from Chapter 6, Chapter 7, and Chapter 8 to merge together to solve this exercise. There is one tricky part of this exercise conceptually, which is making sure you understand which equation you need to solve and to find solutions for. So you're going to generate a figure that looks like this. This is showing here the mean value theorem objective function. I'm leaving this like intentionally mysterious here. It's not the function, it's not the function's derivative. It is the objective function of the mean value theorem. So that's the tricky part of this exercise, to make sure you know what is the right equation to solve for. Okay, and then basically this figure is showing results of the grid search technique that you learned about in Chapter 6. So here is the dotted line is the objective function, and then the black line is the absolute value of the objective function. You will remember from Chapter 6 that when we use the grid search method to find critical points of a derivative, then we take the absolute value and we look for the minimum points here. Okay, so that's the 3 solutions. Now, once you get these 3 solutions to this mean value theorem objective equation, those are the 3 solutions. Those are the values of b that solve the mean value theorem. And once you get that, then you can finally create this plot. And of course, you'll recognize the style of this plot. This is the same as the plot for mean value theorem solutions that we've been working with earlier in this chapter. So you see the function itself, cos of x squared. You see the secant line drawn between the two interval bounds, and you see the three solutions where the derivative of this function equals, the slope of the tangent line at these 3 points is the same as the slope of this secant line here. All right, so I hope you enjoyed working through this exercise. As I mentioned, there is a lot of code, but a lot of the code that you need for this exercise you can copy from previous chapters and also earlier in this chapter. Okay, this is, in my opinion, the only really kind of conceptually tricky part of this exercise, which is to realize that what we want to solve for in the mean value theorem problem is not the derivative of the function, but is the derivative of the function minus this variable that I call the right-hand side, which is the slope of the secant line. So that comes from, like here and basically earlier in the code when I show the algorithm. Okay, so that is what I lambdify. It's not the function, it's not the function's derivative, it's the function's derivative set equal to the slope of the secant line. Okay, so then we have our approximation. This is a grid search technique, and so we know from explorations and also common sense that the higher the resolution of our x-axis grid, the more accurate the solutions will be. So that's why I'm using 10,000 points here. Okay, and then here I am finding the empirical critical points of this function, so minus the absolute value of the function that we want to grid search over, which is here I call it mean value theorem fun. And yeah, I mean, this code should be familiar from chapter 7. Okay, and then this visualization code is copied from chapter 6. This is the first figure that I showed in the book for this exercise. And yeah, so basically the idea is that we're looking for where the dotted line, which is the objective function, crosses 0. That's the theory. We want to know where this function equals 0. But in practice, a better way to find that is by searching for the minimum points of this, or the peaks of the negative of the absolute value of this objective function. Okay. Now we have the 3 solutions, right? So this gives us the solutions to the mean value theorem problem. At least, these are good numerical approximations. From here, this plot is straightforward. This is actually just exactly the plot or the code to produce the plot for the mean value theorem problem that I developed earlier and showed for, I think that was exercise 2. Welcome to exercise 6 of chapter 8. This exercise is about solving Rolle's theorem problems. So before we've been working with the mean value theorem, and of course Rolle's theorem is a special case of the mean value theorem where we are only interested in where the derivative of the function is 0. Okay, so here is the math function to solve. It's just the absolute value of sine, pretty straightforward. At least it's simple to write out in math. In this interval, so the interval from pi over 2 to 3 pi over 2. Now, what you want to do is basically write SymPy code to follow through the steps for solving Rolle's theorem problems that I outlined in this section, and I'll scroll up to that in a moment. But basically, you're going to get stuck with SymPy, and so therefore you're going to need to proceed. I call this the old-fashioned way. You're going to solve this problem, so Rolle's theorem problem, to this problem with this function and these bounds using paper and pencil. So you want to do that before worrying about continuing with Python. Here is a figure from the book that illustrates Rolle's theorem. So given some function, as long as it is continuous and differentiable, given 2 points, xa or x equals a and x equals c, these are the bounds of the interval that we are considering. Rolle's theorem tells us that there is at least one point between a and b where the derivative equals 0. Okay, so I discussed this earlier in the chapter. And so now what we want to do is find this point B using SymPy. And yeah, essentially SymPy is going to be unable to give us an exact solution for the math function absolute value of sine. First, I'm going to illustrate that SymPy is going to have problems solving this function, and then I'll go back to the text and show you my manual solution, my old-fashioned solution to Rolle's theorem for this equation. Okay, so the equation is the absolute value of sine, and here are the two bounds that we are interested in. So the first thing we want to do is confirm that f of a and f of b are the same. This is part of the definition of Rolle's theorem, that f of a equals f of b. Sorry, actually, it should be f of c. My apologies. F of a equals f of c, and if that condition is true, and if the function is continuous, then we will be able to find a point in between pi, in this case, pi over 2 and 3 pi over 2, such that the derivative equals 0. Okay, so this is confirmation that these two values are the same. Now, notice that I actually created these bounds in NumPy and not in SymPy. You could also write these out in SymPy like this. That's also fine. In fact, that's probably the better thing to do in this particular case for setting up this problem. Although later on, in a few moments later in the code, I'm going to actually need these to be floating point numbers and not symbolic numbers. So that's why I leave these as numpy.py. Okay, so far so good. Now what we want to do is find the derivative. And here, let me just show you that we do get the derivative. Ignore this thing, that's just the output of display. That's this here. So this just shows you that we get the derivative. This you can actually calculate on your own. We have a composite function, so the sine function, inside the absolute value function. So we use the chain rule, and that gives us the sine of the or the signum function of sine times the derivative of sine, which is cosine. Okay, so that's the chain rule in action. And now what we want to do is solve this expression to for 0, and that's going to tell us the x-axis values at which Rolle's theorem is solved, which means where we have the derivative equal to 0. Okay, now you see it took it took several seconds to run, and it didn't actually get through it. So no algorithms are implemented to solve the equation. Fine, no problem. So now what you need to do is put away your computer, get out a piece of paper and a pen, and solve this problem on your own by hand. So here, these first two equations, this is just confirming that f of a equals f of c. And then here is where we set up the problem. So this is the derivative of the function, which you also saw in SymPy. Here we set it to 0, and then we just solve. So, you don't actually need to solve for x. You can just use your understanding of trig functions to know that when either the sine or the cosine equals 0, then this expression is true. Okay, so we have the product of two terms. When one of them is 0, then the whole thing is 0. So when is sine or cosine equal to 0? Well, it happens when x equals 0 and pi over 2 and pi and 3 pi over 2 and so on. Infinite number of these solutions. Now we know from just from Rolle's theorem problems that we don't actually care about all of these, the infinite series of solutions. We only care about the solutions that are within the interval bounds that we are given for this problem. Okay, but they're all outside the interval except for x equals pi. But is that really the solution? Okay, obviously we should wonder if this is really the solution given that I wrote this question. Let's see what the graph of this function looks like. Okay, well, so here you see the function is the absolute value of sine. Here you see A and C, and visually it certainly, appears that these two values are equal to each other. So far, so good. The problem comes from looking carefully at the solution to Rolls's theorem. Now, it turns out that the solution is a cusp. And what does that mean? That means that the derivative does not exist at that point. The function is continuous at that point, at x equals pi, but there is no solution to Rolls's theorem because the derivative is not defined over this entire interval, which is one of the conditions for Rolls's theorem to be true. Okay, so it violates what I refer to as condition 2 earlier in the text when I introduced Rolls's theorem. Okay, so in fact, there is no solution to this particular problem. Okay, so now the rest of this exercise is basically just to create this plot here. And in particular, I would like you to use numerical approximations to find where this point should be. So not just plotting this function based on a known value, but finding an empirical solution to this problem here. Okay, let's see. Here I'm just making a quick and dirty plot of the function in the bounds that we are given. So this is what we need to specify. These are the two interval bounds, and yeah, Rolls's theorem, or the problem here, is to find a point between this value and this value where the derivative equals 0. Now, you can see also from visual inspection that this is not going to work because we have this the point here where the derivative does not exist. Okay, but based on this plot, it's easy to find the minimum value where the derivative is as close to 0 as it gets, although it's not going to equal exactly 0. Okay, and so yeah, I'm doing this with a simple grid search method. And now in this particular problem, we don't need to worry about taking the minus absolute value of the derivative and finding putative critical points and searching through the critical points and so on. And that's really just because from visual inspection, we know what the we know what the solution is going to be, and it's going to be pi. Okay, so then here is just some plotting. I lambdify the function so I can get numpy values for the visualization. Okay, so and then I plot the value of the function for the two bounds, a and c, and here is b. This is the reluctant to call it the solution to Rolls's theorem because it's not a valid solution because the derivative does not exist at that point. But it is the point in the function that is as close to a solution as we can get, given that there is no true exact solution because of that cusp there. Welcome to exercise 7 of this chapter. I felt that the previous 6 exercises were a bit heavy. They were a lot to do. It was a lot of coding, a lot of concepts, a lot of integrating different concepts across different chapters. So I thought I would have this exercise be a little bit more kind of simple, a little bit more fun, a little bit more enjoyable. This is not so deep into calculus, this exercise. It's really just about having some fun and playing around with math functions and visualization. Okay, so the question is, what happens when you take iterative trig functions? And what I mean by this is instead of just taking the sine of theta, we are taking the sine of the sine of theta. And if that seems interesting to you, then why not go one more step? How about the sine of the sine of the sine of theta? Okay, so that is the goal of this exercise. Write a for loop over 10 iterations and take cosines repeatedly and sines repeatedly. Okay, so what do I mean by this? The first iteration of this for loop is just y equals cos theta. And then the second iteration of the for loop is y is the cosine of the cosine of theta. And then the third iteration is 3 cosines deep. And so on until you get to the 10th iteration where you're taking the cosine of the cosine of the cosine of the cosine, and so on 10 times. Okay, so you do that for cosine and you do it separately for sine, and then you just make some nice visualization. So here is the plot that you will produce. This is theta on the x-axis and y on the y-axis. And here you see that all the lines correspond to iterative cosines, iterative sines, where I'm using darker line colors for each successive iteration through this for loop. So the lighter, so this lightest gray line, this is for the first iteration. This is simply y equals cosine theta. In this case, y equals sine theta. And then each time I iterate over and over, the lines get darker. So it's pretty neat to see what happens with the cosines versus with the sines. And then here, this is just, a fun way of plotting these two functions. Instead of having theta on a particular axis, so being plotted explicitly, I'm plotting the cosines on the x-axis and the sines on the y-axis. Okay, so this light gray circle here, this corresponds to the cosine of theta by the sine of theta. And then the next line, which is a little bit darker gray, that's this one here, that is the cosine of the cosine theta on the x-axis, and the y-coordinates are sine of sine theta. So I hope that makes sense. I hope you enjoy working through this exercise and have some fun with it. Change the colors. Maybe you want to change the functions. Maybe you want to see what happens when you do alternating signs, like the cosine of the sine of the cosine of the sine. Maybe you also want to include powers in here. So the first iteration would be just the cosine of theta. The second iteration might be the cosine of cosine squared of theta. The third iteration could be the cosine of the cosine cubed of theta. Do whatever you want. Just play around, have fun, and continue exploring and visualizing. So here is what my solution looks like. I set x to go from, actually, maybe I should have called this theta because that's what I called it in the function code in the book text. But it goes from 0 to 10 pi in 1001 steps. Here I am initializing the iterative functions. So yc is y of cosine, ys is y sine. Okay, and then you can see I'm initializing them to be just exactly the same as x. I will show you why I do this in a moment. And then the reason why I'm adding zeros is just to make these fresh copies, right? So if I would say yc equals x, that actually doesn't create a new variable called yc. It just creates a new pointer to the same variable. So that would mean if I left the code like this, then when I change this variable, I'm also changing this variable, which I don't want to do. So you could explicitly create a copy by using the copy module in Python. But if it's just numeric data, a simpler way to do that is to add 0, and that just guarantees that this variable and this variable really are distinct. We can change each one independently. Okay, that's just a little bit of like Python computer science stuff. Loop over 10 different iterations. And now you can see that I'm overriding the cosine and the sine function. So yc equals the cosine of yc. Now on the first iteration, on iteration 0, then this is just going to be the cosine of these numbers here from 0 to 10. And then on the second iteration, it's going to be the cosine of the cosine, and then, and so on like this. All right, so then, here's where I just define the color values. I'm using numpy.full with 3 as the first input. So this is going to create a 3-element vector. And all 3 of those elements are equal to 10 divided by 12 minus I divided by 12. So why did I pick these values? Just playing around. This gives me color grayscale that I thought looked good in the plot. There's also no like mathematical motivation for this, just scale numbers between roughly between 0 and 1, but not getting to exactly full white, because then it just disappears from the plot.